Hello and welcome on my YouTube channel. This is today about rethinking vehicles and transport, and the big question is here, could we have more efficient vehicles? What is the content? We have a part A, so this is the video for part A. Part B comes in a second video. And part A is about basic physics and equations which are used in the plots afterwards. We are looking at typical values for rolling resistance coefficients. And we are looking then at plots for some vehicles which are on the market and whether all these equations are fitting to the reality. In part B, we have then the evaluation of the pod bike and Acabian vehicles. We try to have a realistic approach for an efficient vehicle. We are looking at results for an efficient HPV, so a human-powered vehicle. And the last thing is here important aspects for good efficiency and a summary. So let's start into the basics for calculation. So this is an equation you may know from the past physics here. Force F is equal to the mass times acceleration. Then the work W is the force F integrated over the way. And if the force is constant over the way, you can also write that it's force times weight. Then the power P, this is the work per time. And if you have a constant work per time, then you can also write work divided by time. And this is equal to force times speed, because if you substitute work by force times weight, then you can write force times weight divided by time, and weight divided by time is then the speed. Consumption per way. So this is the power integrated over the time and then per way. And if we have then here also constant relations, we can write that the consumption per way is power times weight divided power times time divided by the way. And if you substitute the thing from the previous line, then you have the force. And this is a very convenient thing here, that for a constant speed, you can write that consumption per way is equal to force. The last equation which we need here is the kinetic energy. So this is 1/2 times mass times speed to the power of 2. These are the basic equations what we need here. And if we have a plain road, so if it is not windy and not rainy, and we have constant speed, we can define the drive force here. And what you can see here, we have two terms here. The first term is associated with the mass and the rolling resistance. And the second term is associated with the wind resistance. And you see here, CR is the rolling resistance coefficient, M is the mass, G is the gravity acceleration, CW is here the wind coefficient or the drag coefficient, A is the front area of the vehicle, Rho, this is the air density, and V is the speed. And you already can see here in this equation, so you have a constant part here, which is independent from the speed. And the second term is depending on the speed, and it's related to the speed to the power of 2. But before I go to the next slide, I would like to ask a question here. If you have 1 cubic meter of air, what do you think, what is approximately the weight for this cubic meter air. So is it the weight of 1 pinch of salt, or 1 grape, or 1 apple, or 1 pound of coffee, or 1 liter water? We will see in a few seconds what will be the answer. So I'm doing here the calculation with the Apple iOS application Calca. So this is quite convenient here. And here again you are seeing the parameters which are used. G, the acceleration due to gravity, which is 9.81 meter per square seconds. And the second thing you see is rho, the air density. And here you see it's 1.5 kilogram per cubic meter. So 1 cubic meter air has a weight of more than 1 kilogram. So this is more than 2 pound coffee and more than 1 liter water. Did you think that? Yeah. Then again, CR is the rolling resistance coefficient. The mass is always the vehicle weight plus the driver weight. This plays a role if the vehicle has a low weight, for example, as in case of a scooter. You have the drag coefficient, you have the area, and this is the wind-associated front area in square meter. Then I have the parameter t. This shall be the time for the acceleration from 0 speed to a defined speed in kilometer per hour. And then I have eta, because we have no perfect conditions, and therefore we need an efficiency factor from the battery to the wheels, or from the battery to the tires. And what you are seeing here are 7 equations. So the first bunch is concerning consumption, so battery energy per 100 kilometer at constant speed. We have the input parameters V, the speed, rolling resistance coefficients, mass, drag coefficient, area, and eta. And yeah, this is the same equation as you see in the previous slide. I've added the efficiency factor eta, and here I multiplied with 100 kilometer because I want to have afterwards the consumption per 100 kilometer. And the second and third equation is only that we want to have the consumption only due to the friction and only due to the wind resistance here. We see afterwards that this is beneficial to have this force, this consumption separated here. Yeah, the second bunch of equations is concerning the power. Also here, the total power for constant speed. Yeah, this is then just multiplied with the speed v for getting the power. And also here we have the separation in a power which is needed for the friction and a power which is needed for the drag or for the wind resistance here. The last equation is the battery power which is needed to get from 0 to the defined speed v. And what we are seeing here, this is the kinetic energy divided by the time. And here we are dealing with the other power which is needed if you have the constant speed. And we will see afterwards that these equations are fitting quite well. Let's look at some rolling resistance coefficiencies. Yeah, sorry that this page is in German, but I will explain what it means. So these are here car tires on asphalt, and here we have about 11,000 until 15,000. But a typical value for normal cars, for normal sedans, is here 12,000. Then we have bicycle tires on asphalt. This is this value, 7,000. So approximately the half of car tires on asphalt. Yeah, and here in the middle you have tires on asphalt for trucks. So this is somewhere in between. But I think the most important coefficients are for cars, which is about 12 thousandths, and for bike tires, which are 7 or 6 thousandths. So you maybe have also racing bike tires. So this is then again reduced in the rolling coefficients because the width of the race tires are so small, and then you maybe have even only 3 or 4 thousandths for the rolling coefficient. Here's the first graphic, and you can see here we have the electrical vehicle Tesla Model S. We are assuming a rolling consistence coefficient of 12 thousandths. We have a mass of 2,200 kilogram, and I'm assuming here an efficiency factor of 0.81. Yeah, why 0.81? So I'm assuming that I have 10% loss from battery to the electric motor, and also from the electric motor to the wheels or to the tires, also 10%. So this means 0.9 times 0.9 for the factor, and this is then resulting to 0.81. And what we see here in this graphic is the blue line is the total consumption. The green line is the consumption only to the drag. And the violet curve, this is not really a curve, it's a line. And this is the consumption due to the rolling resistance. And you see this is constant, independent from the speed. You have always a consumption of approximately 9 kilowatt hours. And you see here at about 96 kilometers per hour, this consumption due to wind and due to the rolling resistance is identical. Yeah? So approximately 9 kilowatt hours. So even if you only ride 7 kilometers per hour or less, even in that case, you have already a consumption of approximately 9 kilowatt hours. And this is related to the weight and to the rolling resistance here. The next example is also for the Tesla Model S, but here we are looking at a speed of 130 kilometers per hour. And what is the consumption for that case? And here we have approximately 25 kilowatt hour per 100 kilometer. And this is also values which I see from users here. So about 24, 25 kilowatt hour consumption here per 100 kilometer. The next thing is the comparison between the Tesla S, the Tesla Model S, and the Hyundai Ioniq. This is one of the first Ioniq cars from Hyundai. And what is interesting here is because the two cars have approximately the same parameters. Yeah? So the drag coefficient is almost the same, and also the front area is almost the same. So the difference is only here in the mass. The Ioniq at the beginning had a very small battery, and it has only a 1.5 ton weight here, and the Tesla has 2.2 tons of weight. And yeah, you can see here they are quite nearby, these two curves. And here at 80 kilometers per hour, you have a consumption of 12.1 kilowatt hour per 100 kilometer. And you see in the description below, you see a link where this YouTuber Bjørn Nylund has measured in Norwegian this consumption exactly. So this means the equations are fitting, and also this efficiency factor, I think, is with the right value here. The next thing what I did here is I compared the Schooner Uno here also with a Jupiter 11. So these are two German companies which are building scooters. And you see here for the Uno, first of all, this mass is of course very reduced. I'm assuming always a driver weight of 80 kilogram. And the dramatic thing here is the drag coefficient, because this is very, very high for such scooters. So approximately 6,500 hundredths. This is much, much more than for a Tesla, because this has a shell, and here you have only 25 or 24 hundredths for the drag coefficient. The area is of course smaller here, but the bad thing here is the drag coefficient for such vehicles. And for 50 kilometer per hour, this is the maximum speed of the Uno vehicle here. You have a consumption of about 2.8 kilowatt per hour. And this is what I can also see here, because I'm owning this scooter and I have a 1.4 kilowatt hour battery in this vehicle, and I can drive about 50 kilometer with that. So this is also a very good fit here. The next thing is to see the vehicles, the Uno and also the Jupiter 11 vehicle in a other speed area, for example 75 kilometer per hour. And you already see it's not anymore 2.8 kilowatt hour, it's 5.8. So this means that you need very big batteries if you really want to drive with such vehicles above 50 kilometer per hour. The next, what I did check is how about acceleration. So this was one of the last equations, what we had here. And here again for the Tesla Model S, and this is one of the first Tesla models which achieved from 0 to 100 kilometer per hour in 2.4 seconds. And you can see here then in this curve, if you want to reach this 2.4 seconds, you must need a power of approximately 450 kilowatt. So this kind of power is needed, and this is also exactly what has been available here. I think it was 440 or 450, something like that. So this fits also very, very well. And then again, an acceleration for the scooter Uno. Here I'm only measuring the time from 0 to 45 kilometer per hour. And by the way, I have here a rolling resistance of 15 thousandths and not 12 thousandths, because this scooter has a little bit more friction than cars from my point of view. So it's not very high quality what is built here. And therefore I'm saying that this rolling resistance is a little bit higher here for the overall friction here, what is present. And what we see here for the acceleration, so if we want to drive here from 0 to 45 kilometer per hour, you need 2 kilowatt if you want to do this in 16 seconds. And this is also what I have measured for my scooter here. So it's about 16 to 17 seconds. So this is also a very good fit. Can we do better? That's the question here. And I think definitely yes, because if you look at this figure here, this is the so-called boxfish. And this boxfish has a drag coefficient of 6 hundredths. So not 65 hundredths as for the scooters, or 25 hundredths or 24 hundredths for vehicles. we have here 600s. So this is much, much better here. And this will be subject of our second video and the second part. What can be done better here? So thank you for now, and I hope we see us again in the next video where we evaluate vehicles like the pod bike, or also the Acabian vehicles. Thank you, and see us again in one of the next videos. Bye bye.